And now for a quite interesting comparison about uranium ores. You probably remember this one. It is some rich pitchblende with the thick blisters. You can see it's a really thick layer of pitchblende. All the black stuff here is pitchblende, likely on granite host rock. And that's a primary uranium ore. So as you probably remember, it's quite hot. This piece here is secondary uranium minerals, called in general just gumite. It's a mixture of all kinds of secondary minerals. And this is just a rock that is from the same area, but it's some granite, I suppose, with iron content. So it's somewhat heavy as well, but it's not radioactive. I will use it to compare the weight of these two rocks actually. So if you take a look at these two pieces, they're roughly of equal size. You can see they're about as high as well. The one on the left is a bit bigger in total. So you can see here, just a tiny bit bigger, but they're roughly about equal size. And now let's see what their weight is. This iron containing granite weighs 61 grams. And this secondary uranium minerals piece here weighs 72 grams. As I said, that's secondary minerals, so there's a lot of like calcium and whatever other elements in there as well. And here's that thick pitchblende. You can see it's much smaller than this one. And it's still quite heavy with almost 36 grams. So, what do you think will be the hottest piece here? As I said, that is primary uranium ore. So you can see the rich blisters here and stuff. Or just a mixture of all kinds of secondary minerals, which contains a lot of other elements as well. They are both from Saxony, as I said, so there's no real difference in the geographical settings. Let's see. Let's start with the pitchblende. You can see the pitchblende is about 50, an average of about 50 microsieverts per hour with gamma radiation only. And if I switch over to beta and gamma, you can see and hear that it's a lot more. About 217 microsieverts per hour. So let's see what it's like for those secondary uranium minerals here. That's gamma radiation only. Now you can see we have over 100 microsieverts of only gamma radiation. Around 110 microsieverts even. And if I switch over to beta, you can see we have a good 250 microsieverts average probably. 266 now. Yeah, probably 250 average, I'd say. So what I think is really interesting is that this pitchblende here emits about 50 microsieverts an hour of pure gamma radiation and 270 microsieverts of beta and gamma radiation. So the softer and less penetrating radiation in combination is a lot more, you can see. But if you take the secondary uranium mineral, you have 110 microsieverts of gamma radiation and 260 microsieverts of gamma and beta, or softer radiation in general. And I think that's really amazing, because relative to the amount of gamma radiation here, there's a significant increase in the pitch blender, while the secondary uranium mineral emits much more hard and penetrating radiation. But as for the softer radiation, if you take the softer and the harder radiation together, it emits less than the pitch blender. And that's really interesting, I think.